Okay, so hello everyone. We'll continue with the lecture, and so we will prove something called separating hyperplane theorem. And the theorem statement is as follows. So suppose there are two non-empty disjoint sets. Okay, they are also closed. If you don't understand closed, then you can forget it for the moment. Okay. And so if they are disjoint, so C intersection D is empty. Then it says that there exists A not equal to 0 and B such that A transpose X is less than equal to B for all X in C, and A transpose X is greater than equal to B for all X in D. In other words, the hyperplane A transpose X equals to B will be the separating hyperplane for the sets C and D. Okay, so this is a geometrical result, as you can see. And what is this saying? It's saying that suppose there are two convex sets and C and D, and they don't intersect. Okay, so let us say these are the two convex sets C and D. They don't intersect. Then there exists A not equal to 0 and B such that A transpose X is less than equal to B for all X in C, and A transpose X greater than equal to B for all X in D. So this essentially means like I can have a plane with normal A. So this is the separating hyperplane A transpose X equals to B. Okay. So this is what this theorem is trying to say, that there will exist some A which is normal to the plane and B such that this will act like a separating hyperplane, okay, for C and D. Okay, so this criteria that is written here is just to say that for any point C here, A transpose X will be less than equal to B, because so this will be the half space on this side. So this is the half space A transpose X is less than equal to B, and in this side we have the half space A transpose X is greater than equal to B, but we are saying all X in C, so then it will boil down to only those points which are in here, and all those points which are here will be greater than equal to B. Okay, so this one. So what this is saying is that if you have two convex sets, then there will necessarily exist a hyperplane separating the two. Okay, so we may be curious here to say that what happens if we don't have this convexity condition, right? If you don't have, then I can create a two sets such that the hyperplane won't exist. Okay, and for me it is enough to claim that only one of the set is not convex. Okay, so C and D being convex is a necessary condition, right? Because so I can give a counterexample with a diagram. Okay, so this is C, and another convex set I can take is something like this. Okay, so this is D. So now I cannot have any hyperplane that can separate these two sets, right? Because hyperplane is a plane, right? So it's something straight. So I cannot find. So I do this. It's not possible. Okay, I try to do this. It's not possible because it's going through the set C here. Okay, so there is no way that I can I can find a hyperplane. Okay, so no hyperplane exists. Okay, so this is the existence result of a separating hyperplane theorem. Okay, so let us try to prove this. By proving this, a little bit of maths will be recalled here. So let us try to prove this theorem. Okay. So this is what this diagram says, like what I said just now. Okay, and this is where one of them is not convex. and this is convex. But you could not find any separating hyperplane. Okay, so here I'm going to prove the separating hyperplane theorem. So proof of separating hyperplane theorem. Okay, so what we are given is that C intersection D is empty. Okay, and C and D are convex. Okay, so we can let us say we can draw a line like this. Okay, C and D are convex. So what does this imply? So far, like we have written what we have. Okay, now what I will do is I will define something called a distance. Okay, so I will define a distance. So this is a distance function between C and D as the infimum. Well, this is how distance between sets are defined. Infimum of U minus V to norm, where U is in C and V is in D, right? So as you can see, this is the distance function, and what this is trying to, yeah.
Sir, it would be supremum, right? Why it is infimum?
No, so I'm looking for the smallest distance, right?
Okay, fine, sir.
Yeah, I'm looking for the smallest. So the way way we define the distance between two sets is the smallest possible gap between the two sets. So it should be like infimum. Okay. So so this is the distance between two sets. That's the generic definition between two sets. As long as like you can compute these norms. Okay. So there must be some kind of a vector space C and D. Okay. So the distance function is positive. It is positive because this involves infimum of the norms, right? So this is always a positive number distance. Now, so there will exist some point C in C and D in D that will achieve this distance. So there will exist some point C and D for which we will get this distance. And the reason why we can do this is because here actually the closeness of C and D is needed. Okay, I have not defined the closeness, but I can give you an intuition of why. So as you know, closed set and open sets on the real line at least. So for instance, this is an open interval, whereas this is an closed interval, right? So let us say I give you two sets. Let us say C was the set 0, 1, and let us say D was the set let us say 2, 3. Okay. Now, what is the distance between these two sets? So distance between C and D is the infimum of the set of points. Okay, so U minus V, two norms, right? And U is in C and V is in D. So that's the distance. So what is the infimum in this case? Last time we did infimum. What do you think is the infimum? What is the answer in this case? The distance?
1.
Yeah, so the distance is 1. Okay, why you thought it's 1? You see, so how you go about this, right? You see that there are points here where let us say it's like 0.9 some point. Okay, and because 1 is not in C, so 1 is excluded. That's what the open interval means, right? Here also 2 is excluded and 3 is excluded, right? but the points that you have inside C are something like 0.9, and here the points you have are something like 2.1. Those kind of points are there, right? So if you take differences of those very close points to 1 and very close points to 2, you are not allowed to take 2 exactly, you're not allowed to take 1 exactly. Okay, so you will see that you will get a sequence. So I can so you will get a sequence like this. Okay, so let us say it's like 0 0.9, 0 0.99, and so on, 0 0.999, and so on. Okay, so these are the, like, if you start computing the distances by taking some of the points here and so on, so this is the set you will get of the distances, right? Um, so and apart from all this, you also have points which are like very large, right? So for instance, there are other points like 3, let us say 2.5. Okay, so 2.5 and 2.7, something like this. Okay, so this is the set containing all this, and what we are asking for. Okay, I think I'm making a mistake here. So the set of distances that I'm computing here look like 1 point, let us say 1 or 1.01 or something like this. Okay, 1.000 something 1 or something like this. Okay, so these are the set of things, and then the infimum of this set is the smallest of the lower bounds. So smallest of the lower bound is this 1. Okay, so that's how we got the infimum of this. Okay, we take all possible the thing, and we don't exactly get 1. Okay, because 1 will be when I do 2 minus 1. Okay, so if I draw it on the line, then I have 0 here, I have 1 here, I have 2 here, I have 3 here. So this open interval is here, and this open interval is here. So the distance between them is this. It is like so the way it is defined is the infimum of this. Okay, so this is what you're going to get, and you also distances that you have are, you can take arbitrary u and v, but those are larger. The smallest one that you will get is like 1. Okay, so we consider this set, and then the lower bounds, of all the lower bounds, 1 is the least of the lower bound of this. Hence 1 will become the distance between these two sets. Now coming back to this, the reason, but in this case the infimum and supremum always exist. So in this case we are talking about infimum, and infimum does exist, but the problem is that I don't get exactly a point here and here for which that infimum is obtained. Okay, so that's the thing here. Okay, whereas if it was a closed set, if C and D were closed sets, so let us say C and D were like this, C was this and D were this, then distance between them is still 1, and there exists a point in both the sets which is C, and in this case it's D, such that for which the infimum is achieved. Okay, and it is happening because these are closed sets, because the boundary points are included here. Okay, so on a real line closed set, I have not defined closed set, but on a real line closed sets are nothing but closed intervals. Okay, so that's the intuition I have given you, that on a closed set, you will achieve the infimum. Okay, so the infimum of a closed set is actually the minimum element of the set. In other words, that element will indeed exist there. Okay, so with this intuition, without going into too much detail, so C and D are closed sets, right? So C and D are closed sets. Okay, this implies, so you just imagine like this: if C and D were closed sets, then there will exist a C in some element C in C and D in D, for which if you subtract, okay, and take the norm, then that infimum is achieved, right? So there implies there exists C in C and small d in D, such that achieves achieves the distance of C, that achieves or that is equal to the distance of C and D. Okay, so that is happening because of the closed and boundedness property. Okay, so that's also we needed. Now now what I will, so remember our goal is to prove that there exists a separating hyperplane, right? So if we could produce that hyperplane, that would be nice. Now, if we look into the intuition of how we can prove this result, okay, I mean, this has to be convex and like this, then if we have a hyperplane, then the situation could be like this. If there is a point here, there is a point here, let us say this for which the infimum is achieved. So this is like C and D. That's the closest point between the two hyperplane according to this distance function. Then our intuition suggests that the hyperplane could be a line that is perpendicular to CD. Okay, so this is the line joining CD. And if I can find a hyperplane that is perpendicular, okay, this is not a straight line, but I intend to make it straight. So let us say this is like this. So our intuition suggests that if C and D are convex sets and small c and small d are the points that are closest to each other, then the possible hyperplane is the one that is perpendicular to the line joining C and D. Okay, so this is something we will keep in mind because that is what this is. I mean, as I said, intuition is always very important. Okay, intuition doesn't mean it's a bad thing. Okay, intuition is the place where everything starts. So first you have to think have intuition. So let us check this intuition, right? Whether it will be true or not. In other words, if there is a plane which is perpendicular to C and D, and if this is a plane, then it must be, or in other words, the normal to this plane will be along the line joining C and D. Okay, so it will be some, let us say C minus D, right? So this is the line this, and then so it seems like the plane that I'm going to get will be the plane with this normal. Okay, so you keep this in mind, and this is what we are going to use now to prove our claim. So let us go to the next page. So we define, so with this intuition we define the normal to be D minus C or C minus D, it doesn't matter. Okay. Okay, so and then we define B to be as follows. B to be 2 norm of D whole square, C 2 norm whole square. The choice of this will be clear as we go along, because this choice of B will make sure that A transpose X is less than equal to B for the points in C, and A transpose X is greater than equal to B for the points in D, which is what we want, because the C should be on the left half space of this plane, and so this will look like a well cooked, but these things usually happen when you actually keep working and then come out with this. So in this case, I have put this up front, but we will see what is the role of this, how it will make sure that C lies on the left half space and D lies on the right half space. Okay, so with this definition, so what I said is like I have to claim that this is so claim is the following: fx, which is A transpose X plus B, okay, which if we write this in the using the values of A and B, which is D minus C transpose and And yeah, so the way I will write is as follows. So we will double check again. So this is like half of d plus c. Okay. So let us check this. This is indeed equal to A transpose X plus B. So I have substituted A to be D minus C and B to be this guy. And I claim that this is nothing but the same thing. So it is true because in place of A, I wanted D minus C, right? So I do have D minus C transpose X. So this is D minus C transpose X. And the half is there. And this guy, D minus C transpose times D plus C, we can check that this is nothing but the numerator. Okay, so D minus C transpose plus, because the way this is defined is like this. Okay, because C minus C transpose D and D transpose C will cancel, right? So this is like D transpose D minus C transpose D. Yeah, plus D transpose C minus C transpose C. So this cancels because C transpose D is same as D transpose C, just a number, right? Transpose of a number doesn't make sense. This is like norm of D whole square minus norm of C whole square. Okay, assume two norm. So this indeed is that. Okay, so we have written in this form. Now, so our claim is that this is non-positive. Okay, in other words, claim is that this guy is non-positive, that is less than equal to 0 on C, and this is greater than equal to
Sir,
0
won't it
on
be X plus half?
where?
X plus half times D plus C.
Is this like a plus or minus, right?
Yeah, like X minus half you written, right, sir?
Yeah,
It won't be. It will be X plus half, right?
yeah, let us see. Let us check again, like is there a, so D minus C and D transpose D, yes, and then minus C transpose D plus D transpose D, and then minus C transpose C, yes. So there is no sign from there, and yeah, that seems to be, it should be like plus. Yeah, seems to be plus. Then it will make sense. Or I could take this minus here, okay, and then I can have a minus here. Okay, so let me keep it like this. I take a minus b here. Okay, for a bit of simplicity that we will be seen now. Okay, so and this is d. Okay, for a hyperplane it doesn't matter. I took place b minus b, it doesn't matter because b is just like intercepts. I can take a minus of that, minus of that. Doesn't matter. Okay, but yeah, for but I can surely work with plus also, and it should also not break the proof. Okay, so that should be fine as well. Okay, so this is what we want to prove. Okay, so this is what we are claiming, hyperplane, and then this is on the left side, so it's less than equal to 0 on C, and this is greater than equal to 0 on D. Okay, so what do we do now? Okay, so f, let us prove that f is non-negative on D. Okay, so it's like two parts are there in the proof. One, if we prove, other should follow from there. Okay, so let us prove that. Let us prove the claim 2. So f is non-negative on D. Okay, so suppose u is in D. Okay, so if u is in D, then f of u we would like to know, right? So f of u, so what we have to prove is that, so we have to prove that for any arbitrary u, okay, so what we have to prove is f of u, okay, is greater than or equal to 0. Okay, this is what we have to prove. We have taken any arbitrary u and we have to prove that f is non-negative on D. Now we will prove this by contradiction. Okay, so proof by contradiction. So suppose f of u is less than 0. Okay, so on the contrary, suppose f of u is less than 0, then I should arrive at something contradictory. Okay, so what will happen, right? So this would imply what? This would imply so I substitute the u there. Okay, if I substitute the u there, then what will happen? So D minus C transpose and u minus D and then plus half of norm of D minus C squared. Okay, so you can see all of you can see this. I substituted u here in place of x, and then I taken out the u and then the inner part is still a half of D minus C. Okay, so so this is like less than 0.
How did right? U minus D come?
I mean, I can add 1/2 D inside, right? I can add and subtract half of D. Okay, so this step is like, so if I go back to the previous step, okay, then let me do that step. So D minus C transpose, and this is same as U minus D, and then it becomes plus half now. Okay, so you agree with this? So this is same as this. Is it or not? So let us check this. So yeah, so D, there will be minus D here, right? Minus half D. Okay, so minus half D, and then I can take minus common, minus half common. So it will turn out to be again minus half of D plus C. So this is okay. Okay, and then so this is less than 0. So all is less than 0 continuing right now. And then I have D minus C transpose U minus D plus half of D minus C. Okay, so the D minus C, so this will become the norm, and this is less than 0. Okay, now this guy is always positive because this involves the norm. So the only way this whole quantity can be 0 is when this is 0. Okay, so this must be less than 0. So this implies D minus C transpose U minus D is less than 0. Okay. Okay, so now up to here is fine. We have to arrive at a contradiction. So far we don't see anything yet. Now we will consider, we will use some calculus trick. So do I have a next page? Yes. Okay. So what we have is, let us go back to the next page only then. Okay. So we had, so we'll just copy the previous thing, had D minus C transpose and then U minus D was less than 0. Okay, now consider the following function. Okay, D. So consider the derivative of this d by dt of D plus. It will look very strange right now. Okay, but I will explain. U minus D minus C. Okay. Consider a derivative of this. Okay, you will see that the derivative of this will turn out to be this, right? So with some factor, right? So derivative of this is how much? How do you take a derivative of this? Remember, this is a derivative with respect to t, right? So this is the t here, right? So just to so what? How do you take derivative of a norm, right? Well, you have to expand this, right? So this is like d plus t u minus d minus c transpose of d plus t u minus d minus c. Okay, so this is the definition of the norm. So we have written a norm x square is x transpose x. So that's the definition of the norm. And then if I multiply it and so on, so what do I get? This is like d by dt. Remember that all those terms that don't involve t, they are supposed to vanish. So I should not do anything with them, right? So I can write, okay, let me do it here. So this is like, so I will pair this d minus c together because they will vanish anyway. So this is like d minus c transpose d minus c, okay, and then plus, and then d minus c will go with the t term. So d minus c transpose t u minus d. And then we will have now this term t of u minus d will multiply with d minus c and then plus t square of u minus d transpose u minus d. Okay, and everything is d by dt. So these guys will go to 0 because there is no t involvement here, and remaining all have actually t. Okay, so if we take the derivative of this, what do we get? And what do we get, right? So if we take the derivative of this, we get 2 of this because they are the same term, right? U minus d here should be transpose. Okay, so they are the same term, right? So this is like 2t okay, so it's like 2t and d minus c transpose u minus d. So this is still d by dt. I have not done d by dt yet, and then plus t square u minus d transpose u minus d. Okay, so now if I want to compute this, so if I like do this, then what do I have? It's like 2 of d minus c transpose u minus d plus 2t of u minus d transpose u minus d. Now what I want to see is how does this derivative behave at 0. Okay, so I want to compute this derivative at I want to compute this derivative at 0. Okay, so what happens at 0, right? So let us go to the next slide. Okay, I think I don't have space. Okay, let me finish this here. So if I evaluate this derivative at, so d by dt of d plus t u minus d minus c square evaluated at t equals to 0. If we evaluate this as t equal to 0, it comes out to be exactly this, which is 2 d minus c transpose u minus d. But from what we have found here, this will imply that this is less than 0. Now derivative of this quantity is less than 0, right? Around t equals to 0, right? So this means what? This means that the function must be decreasing there, okay, at t equals to 0. I mean, very in an area very close to 0. Okay, then the function must be decreasing even for the slightest area. It could be a very slight area, but it's supposed to decrease at 0. Okay, in the immediate, that's what the derivative tells you, right? In the immediate future of t equals to 0, the derivative, the function is going to decrease. Okay, so this function, it tells you that this function is going to decrease in the immediate future of t equals to 0. Okay, so that's what we have. So what does this mean? So this means that there exists some t node just greater than there exists some t node like small enough, let us say small enough, t small enough such that we have the following. Okay, so such that this guy d plus t u minus d minus c to norm is less than equal to d minus c. Okay, because that's what it sees, it tells us, right? So for a small enough t, we will have this this thing, right? So d plus this is it's going to decrease. Okay, for a small enough t. In other words, it's going to decrease than this. Okay, it could be very small t, that's fine, but it's going to be smaller than this. Remember that you are at d minus c, right? And the function you have is the norm. Okay, that's defined. So function, you have the norm and you are starting at d minus c, and then you are saying, okay, for a slight perturbation around this point, which is this, for t just small enough, you are going to decrease just around small enough t. Okay, so if that is the case, then this is what we have. Okay, so what does this suggest now? If I have this, what does this suggest? What is u minus d, right? Where does u minus d point belong? Remember what was u and what was d? So remember u was where? Remember u was in d, right? And d was in d already, right? So u was in d and the d was in d, right? So where does this point belong now? So u minus d, right? So where does this point belong now? Okay, or like
Inside D, inside D, because
inside
it's
d, or
convex.
actually, yeah, the way I should ask is the following: where does this point belong? D plus t u minus d. Given that u and d are in d, right? So d is convex, right? So this is nothing but it's the line joining d and u, and t is small enough. Okay, so this is in d. So what does this contradict? What does this going to contradict now? Okay, so what is this going to contradict? Okay,
I think this contradicts that there exists some point which is closer to set C than the infimum.
Yes. So what we have found is that we have found another point, which is this in D, for which I even get lesser than D minus C. Remember, D minus C was the infimum that you got. It's like the closest distance. But now you are saying that I found another point which is closer to C, and that point is this, and this is a contradiction. Okay, so you have found a new point closer to C. Okay, a contradiction to the fact that D was the closest point. Okay, so this proves that this proves that What does this prove? Remember how did we start? We started with this being non-negative, right? And we started with a contradictory assumption that this is less than 0. It is now contradicting this. Okay, so it is now contradicting this, and so it's contradicting the fact that that this was the norm, was so even before this, yeah. So it's contradicting the fact that D and U and D, right? Where okay, where is that? C and D, yeah. So C and D, right? Yeah. So this C and D. So C is in C and D is in D, that achieves the infimum. Okay, it's contradicting this. Okay, and we started with this assumption on the contrary, and we arrived at a contradiction that that the D point is no longer the closure. Okay, so that's the contradiction here. So this will tell us that our assumption must be wrong. Must be wrong. That's why we were led to the contradiction. Okay, hence the only other possibility now left is that fx must be greater than or equal to 0. Okay, on D. Now the argument that fx is less than or equal to 0 on C will follow in the same way. You just have to manage the signs and so on, but the argument will be similar. Okay, you will again prove it in a contradictory way. Okay. So this is the proof of the separating hyperplane theorem. So from here we conclude that with our choice of the A, given that we have two convex sets C and D, we can find a hyperplane explicitly with normal this and intercept B to be this, such that it can separate the two sets, convex sets C and D. Okay, so I haven't defined something called open set and closed set, but I can quickly define this. To define open sets, what I need is something called a concept of an interior point. Okay, an element X in some set C is called an interior point if there exists an epsilon greater than 0 for which this happens. Okay, so what do you understand from this relation, right? Like, what does this tell you? So an X is called interior point if there exists an epsilon greater than 0 for which set of all y such that y minus x to norm is less than or equal to epsilon is in C, right? So what this is saying is like an element X in C is an interior point of C if there exists an epsilon ball, right? So let us say this is 2 norms, so it will look like a ball. Okay, such that for all points y, so these are the points y with a distance less than epsilon. Okay, so this is the epsilon radius ball. You can find around x, which is entirely contained in C. And if you can do this for, let us say, another point z. Now I will declare z to be interior point if I can find an epsilon ball. Okay, there exists one, so it's enough to produce one epsilon. Okay, any one epsilon ball you have to identify such that that ball is completely inside C. Okay, so you will imagine like which point won't be interior point. Okay, so as the name suggests, these are points which are in the interior, right? So you can immediately say what are the points here? Well, these points cannot be interior because I can never find a however small ball such that that will be entirely inside. It's not possible. Okay, because it's on the boundary. Whenever I will take even the slightest of the ball, it will always go outside. Okay, so that's why points on the boundary can never be interior point. But it's not only about boundary points because sets can also look like this. Okay, so these are the holes in the set. Okay, so these points also are not interior points. So these are not inside the set, right? So this point is not interior point again. Only these points are interior point. You just go inside and then it immediately becomes interior point, because I can take a small enough ball and it will contain inside the set C. Okay. So examples of this is, let us say we can take an open interval. Okay. Then if I take the 1.1 on the open interval, okay, then 1 is not an interior point, because if the open ball in the real line will be like this, right? No matter however small I take, okay, so it is not the ball containing this is not inside. Okay, so obviously 1 is not an interior point. And even like it's even more interesting for the closed set actually. So closed set, if you take 1 is included, but the moment I take any ball around 1, the whole of the ball is not inside 0, 1. Okay, this is the set C. So in this case, 0 and 1 are not interior points. But any point other than 0 and 1 are indeed interior points, because you can tell very small number close to 0, let us something like this. I can always take a very small enough ball such that it's so let us say that point that you told me is like this, 0.0001. I always have some room to take a small enough ball such that it is inside 0, 1. Okay, so any point other than 0, 1 is an interior point. So in other words, the set of all interior points of 0, 1 closed is 0, 1 open interval, right? So that's the definition of interior points. Okay. Set of all points interior to C is called the interior set of all points interior to C. Set of all interior points of C are called interior of C. Okay. In other words, interior, for example, interior of 0, 1 closed is 0, 1 open. Okay. At set C will be called open set if the interior of C becomes the whole set C. Okay, so clearly 0, 1 interior, if we do, then we get 0, 1. So in this case, interior of this is not exactly equal to the original C. Hence, this 0, 1 closed is not an open interval, open set. But if the set itself was 0, 1, then the interior of this is still 0, 1 only. So in this case, interior of C is equal to C itself. Okay, so the open sets are defined like that. If all its points are interior points. Okay, so open set is a set whose all points are interior points. Okay, so that's open set. Okay, and closed set is just the complement. Okay, so you can use the complement definition. So a C is closed if its complement is open. Okay, a C is closed if its complement, let us say universal set is Rn. So if its complement is open. Okay, and the closure of a set C is defined as follows. So this will look a little bit too much, but I can give you an intuition behind this. Like often we don't need to remember this. Okay, so what it's trying to say is the closure of this. Look, closure from our intuition will suggest like this. If I have 0, 1, what is the closure of this? Well, closure will be one that that includes the boundary points basically. Okay, so the closure of this will be 0, 1. Okay, so closure of this will be 0, 1. Okay, so basically you have to include the points which are on the boundary. Okay, and what are the boundary points? So boundary points are the points. So let us say set C like this. How do I define the boundary point? I have defined interior points. It's like I can always draw a ball and that's inside. Boundary points is also easy to define now. So those points are boundary points. Whenever I take any neighborhood, I always get points both from inside and some points also from outside. Okay, so X in C is a boundary point if whenever we take a ball, let us say any small ball itself, let us say this is the ball, epsilon ball, okay, of radius like epsilon, around X, then if we intersect with C is not empty, as well as if I intersect it with C complement, also it's not empty. Okay, not empty. Okay, so that's how mathematically we can define a boundary point. Boundary points, and if you just go outside this, these are no longer boundary point, because it's like whenever, right, I should be able to take, whenever I take any ball, right, that should intersect interior as well as exterior. So moment you take a point like this, this is no longer satisfied, because I have the liberty to take a neighborhood like this. Now it is not intersecting with anything outside. It's only intersecting with this, and this is the AND condition. This and this, okay, both should be there, and only then. So this point is not the boundary point. Okay. So another way to define a closure would be the set C union the boundary of C. Okay. So that's how I can close. So what were the boundary of this interval? Boundaries were 0 and 1 are boundary points. And if I have to do a closure, then I get this. So basically the set C union 0 and 1, the boundary points I added, and that is called closure. So if you are not comfortable with this, forget this. You just remember the other definition that I told you. So you have interior point, you have boundary point, and closure is the set C union the boundary points. Okay, union these boundary points that I defined here. So with this, let us now. So these are the explanations graphical that I already told you. So this is the boundary point, and this is the interior point. So now you can play with this example just to be clear that you understand these things clearly. So which of the following sets are open sets? Okay, so let us say the set of integer. Okay, so is this a open set? So what was the open set? Open set definition, recall, all points are interior points. Points are interior points, and a point was interior when I am allowed to take. So when a point is interior when I can produce a small enough open ball which is inside the set C. Okay, small enough. Obviously, I should not be taking something like big, right? That obviously won't be inside C, but I have the liberty to choose any ball. As long as I can produce a small enough ball around X, which is contained in C, then immediately I will declare X to be interior point. And a set C is open if all its points are interior points. Okay. So this is the recall that we did. Now focus on this. Is Z the set of integers open set? In other words, are all points of Z? Z is the set of integers, right? So all points like -1, 0, -3, 100, something like that. All points, are they interior points? So what do you think?
Yes, sir.
Yes?
No, sir.
No. Why?
If you take any integer, for any epsilon naught, it won't belong to the integer set, right?
Yes.
For any integer.
Yeah, so let us say this is 0, 1, 2. These are the integer lines we understand, right? So this is the integer line, and what it says is like all points are interior point. Just focus on one point. Let us say 1. Now, the moment I take any epsilon ball, regardless of how small, there are points which are not in the set Z. Okay. So if I take a small enough, let us say interval 1 minus epsilon, 1 plus epsilon. So this is the open ball in the real line. So this is not contained in Z. Okay, this is not contained in Z. Regardless of how small, regardless of how small, however small epsilon is. Right. So regardless of however small epsilon do I, it will always contain something other than integer, right?
Hello, sir.
Yeah. Yes.
So is the definition says for all epsilon or for any
No,
one
no.
epsilon?
For any one epsilon, there exists one.
Yeah. So we can consider an epsilon as one, right?
No, but you can. So there is like -1 and then there is 1. So it should be centered at 1, right?
Yeah, yes, sir. Consider epsilon as 1. Then
Yeah,
1 minus 1, 0, and 1 plus 1, 2 belongs, right?
No, but this is interval, right? All points.
The
from
whole
here-
norm ball should be
Yeah, whole thing
belong
should
to.
be there.
Okay, okay.
You
Yeah,
can
yeah,
take
okay,
1. So this is like 0 and 2. But this is the interval. All things should be there, right? But in integer, we don't have these points, right? So it's
Yeah,
not.
yes, so good. Yeah.
Yeah.
We need to get entire ball. I thought boundary.
Yes, entire ball. Yes, yes. So, and since just for one point itself, it didn't work, that is enough to say that naturally we cannot do it around anything, but it's enough to produce just one point itself. Because in open set, all points must be interior point. I have showed that one is not interior point, hence it can never be open set. Just one point is not interior point means it cannot be open. Okay, so now let us move into second example.
Second is also closed only, sir, because one have no epsilon ball. 1 by 2 and 1 by 3.
Is it open or not? Yeah, okay.
Not, sir. No.
Not open. So the intuition is very similar to what we did before. Okay. So the intuition is very similar. It's not open. Okay, because there are some discrete points already we can see like 1 by 2. So already around 1.5 and 1 by 3. So I can yeah. So it's not possible to create a ball around these guys and keep it inside. Okay, so that's not possible. Okay, so that was similar. What about sine x and x going from 0 to 2 pi? So what is the thing about sine x, right? So it passes through this and then pi by 2. Okay, pi by 2 and then pi and then 3 pi by 2 and then 2 pi. Okay, so okay, so this is like sine x. Now and this is like yeah, so these are the points that's taking. So points it's taking is like max is 1 and mean is -1. Okay, so the points in this set are continuously varying, obviously, because the curve is continuous. So it's continuously varying between 0 and 1. So sine x, because it's like the whole thing, so it's 0 and -1 actually. Sorry, -1 and 1. Yeah, so it varies between -1 and 1. Right, it varies between -1 and 1. So is this an open set?
No, sir.
Why?
Because -1 and 1 are also included, so we cannot draw a ball with 1.
So everyone see this? Right? So everyone see this, right? So the sign, what values, you don't have to focus on the curve, right? You have to focus these points. Sign is taking all this, okay? And sign is taking all these values, right? And so if I take any point here, it will indeed, I can take a ball and that will be inside. By ball, I mean this this interval ball, okay? So the ball looks like a line, okay? Should not do like this, right? Because that's not the ball. Ball in on a line is just this, okay? So as one of you said, the problem is with these points where I am doing this. Whenever, no matter how small I do, I will go out, right? So this is not open set. This is not okay. So far all are not. What about this guy? 0 to pi.
This is not open as well because it is closed because 1 is in it.
So what do you think? Right. Okay. So 0 to pi, right? So the sign is going from 0 to pi up to here, right? So
Yes,
the values that is taking is this and this, right?
Yes, sir. 0
Open
is
or
not in the set, but 1 is inside the set. So 1 is a boundary point, which is not an interior point.
yes. So all of you see this. The maximum value sign achieves at pi by 2, right? So that is inside, because that pi by 2 is inside this interval. So maximum value is achieved, which is 1. So that is like less than equal to for this set. Okay, let us say y belongs to this set. Then the y ranges are like this, and the minimum value in this is 0, but 0 is achieved at 0, and 0 is achieved at pi by 2, and both are not included in the set. Sorry, not pi by 2, but pi. Okay, but both are not included. Hence, the y, the sign of 0, which is 0, will not be included. So this is like strictly less than. So this is like this interval, 0 open and then 1 closed. Okay, so this is not
Sir,
this. Yes.
sir, can you take us to the slide where you defined an interior point?
I mean, yeah, so we can do, but
Yes.
there's nothing.
So
Yeah.
I have yes, sir. Sir, you said there exists an epsilon greater than 0, but it should be for all epsilon greater than 0, right?
No, I'm just saying there exist. Exist means just one is enough, right?
So, sir, in the integer line case, suppose we are taking all the integers, and I will take epsilon as 1, suppose. In the same example, then that number contains 1 point.
So the whole thing should be inside the set. The whole set should be a subset. The whole ball should be inside, right? In your case, if I take 1 minus epsilon and 1 plus epsilon, and you say epsilon to be what? What did you say epsilon to be 1?
Yes, sir.
Okay. So you take, okay, so set epsilon to be 1. So which ball I get? So 1 minus 1 is 0, and then 1 plus 1 is 2, right? Is this inside Z?
No, sir.
No. So that's not true, right? So no matter which epsilon positive you give me, you will never be able to put that ball inside that, because the moment you have this, you will always have some width, no matter how small you are. And we know that those real numbers are not in Z, right?
Yes, sir.
That's the problem. Okay.
Okay, sir.
Okay, so and then okay, so this is the fourth one. So this is not open, like one of you said, because at 1 there is a problem, because 1 is there, and around 1, so 1 is there, and around 1, no matter how small I do, there will always exist something that is going outside. Okay, and hence it cannot completely remain inside 0, 1. Okay, so that is also not the case. Now the fifth one, set of all rational numbers. Okay, set of all rational numbers. Is this a open set?
No, sir.
Yes. Why?
Because the very neighborhood of every rational number would be irrational number. Yes, that is not involved in the set. So
yes,
that is not the open set.
Yes, exactly. Because we know that between any rational number, let us say R1, R2, there are infinitely many rational number as well as irrational number. So regardless of so around any rational number I take, any however small neighborhood, I will always include irrational number. Okay, so any rational number, if I take a neighborhood R minus epsilon and R plus epsilon, so this is the epsilon ball I take. This can never be inside the rational number. Okay, so rational number is sometimes denoted by Q. This cannot completely contain inside, because between any smallest even interval you take, that contains infinitely many irrational also. So you cannot put this in Q. So that's also like no. Okay. You are following, because this is a little bit of analysis. So I was wondering, these are used in some of the arguments that we will see at some point. We will study some of the advanced algorithms for optimizations. So these are some of the things that is assumed, and then yeah, so that's why I'm doing this. So what about this example? Which of the following are open subsets of R2? So is this open? Now these are lattice points, right? So in R2 now we are talking about R2. So R2 plane is like this, and M and N are the lattice points. So these are the lattice points, right? So these are the M and N are integers. So these are these discrete points in space. Okay, this is this set lattice points. So is this open? Right?
No, sir.
No. So it's very simple, right? Because here in this case the ball will look like a disk. So no matter how small I do, the whole thing, the other points just outside is not in this set. Okay, so again, like this is very similar to this, but it's a two-dimensional like this. Yeah, it's a two-dimensional extension of this. This is not. And what about this? This is similar to this. Okay, so you can think that again, this will not be an open set again, because there are the moment you see discrete points and so on. But I must tell you something. It's not just about discrete point. Okay, actually, even discrete point sets can be open. How is that? So let me construct some example before you, so that you will be a little bit surprised, I think. Let's see. Let me consider some example. Yeah.
Sir, here second question, their Mn belongs to real line, right? So it would be an open, I guess.
I think there is a mistake here, I would say, because at 0 it will not be defined, right? So this must be Z here. Yeah, that is Z.
But again, like in R also, the infinite won't be defined, but like we can still make the circle as small as we can, but like at 0 anyways, there is no point, right? So
yeah, it may not be, but there are other difficult points, right? Because 1 by half point, let us say. So if you take a ball around this, it's not going to be around this completely, right? So let us say this is half and this is half. So 0 is excluded here also. I agree, but these points are like, so how are these points behaving, right? Like M is.
no, for R I was saying. Okay, I was saying for R.
No, okay. Yeah. Yeah, so if this is Z,
for R it would be open, right?
For R, but 0 is not included, right?
Yeah, but here also for Z also we are excluding 0, right, sir?
Yes.
Yeah,
So
on excluding 0.
Okay, so you're saying what happens if we have R and whether this is open or not, right?
Yeah.
Yeah, in that case, it will become open, because now M is taking arbitrary values, right? Because I can generate any XY number. Any XY number can be generated, except can be generated. Okay, by taking M is equal to 1 over X and N is equal to 1 over Y, except 0, 0. So it will be like this space where you have this everything included except 0. So that is fine. That is that will be open. Okay, because except 0 you take any You might be thinking, except 0, how come? Well, you can take any point which is very close also. I can always take a ball, and that is inside inside this. So that's fine. Okay, it's like this. So it's like considering this 0, 1 and union of 1, 2. Now this is open. So what is excluded is the 1 here, right? But it's open because 1 I don't have to check for interior anyway. So this is a extension in R2 you can think of. From all possible dimensions, this boundary, in this case the boundary is 0 here. Okay, so union of open sets is open. That's what I'm trying to say. In general, you can prove that union of open sets is open, intersection of open sets is open. So it's possible to do this. So what I was trying to say is like, it's not necessarily, the openness is not necessarily related only with the discrete points. Okay, because it's relative to what I'm talking about. Okay, so open and closeness property is relative to the parent set in reference to what I'm telling it's open or closed. Right, in reference to what I'm saying it's open or closed. For instance, if I've changed this R to Z itself, let us say, I change this R to Z itself, let us say, then what do you say about this?
Open.
Now it becomes open. Okay, it seems strange, right? So it's so Z, a set of integers relative to set of integers, it's open. You see, because now you are looking for your ball inside Z, in Z, right? So set of integers is now is 0, 1, 2, 3, like this, right? -1, -2. So let us fix some point like 1, right? And then you will say that I will consider some open interval. But where is the space we are considering? Our parent space is just Z. Okay. So our parent space is Z, so we have no view of the real number. We forgot the real number. We are just thinking neighborhoods in Z now. Okay, so 1 minus epsilon and 1 plus epsilon. Okay, if there exist an epsilon, right? So the question was what? If there exists an epsilon, so it's like I have to produce one epsilon. Right, such that so what epsilon I should choose?
One.
Yeah, so let us choose epsilon to be 1. Okay, so what do we get in the ball, right? So it's like 1 minus 0 and sorry, so 0 and then 2. Now it is like the set actually. So this open interval now it's like 0. Okay, not 0 but 1, only 1. Okay, because like 2 is not included. Okay, because we are taking open sets, right? Now we have this set. So is 1 in Z? Yes. So 1 is in Z. Okay. You see the point here? Like the open open balls in Z will only contain integers, right? But if we are taking in reference to real number, then there is a problem, because then if our parent set is real number, then we have to include everything between 0 and 2. That's the problem. But if our parent set itself Z, then these inner points have no meaning at all. The ball will look like 1 only, open ball. It will contain only 1, right? So it's also the reference with which we are looking. For example, look into this example. Is this is this open set with reference to Z? Okay, so what if I say that ask whether this set is open in Z?
No.
Why?
Because there is only one, like one, and whatever you take inside it, like we won't be considering any real numbers, right? So there is only one element for Z.
Yeah, I mean, in this case, this is not a good example actually. So let me change for this example. Let me change this to Q, rational number. Okay. Now try to see, because set should be a subset, right? So I should not take. So let us say Q. Now these points are rational numbers. Now what do you think? Is this set open in Q?
Yes, right.
So you think all points are interior points, right? Right?
Like if we consider 1 by n set where n is q, it would be a open, right?
Yeah, so all points should be interior points. That's what I'm trying to say, right? So what are the typical points you have? Like 1 is there, half is there, 1/3 is there. So this is the set and it's tending to 0. It's not 0 exactly, but tending to 0. Okay, 0 is not in this set. Okay. So we can say that it's tending to 0, something like this. And then we have to check that all points are interior points, right? So what do you think? What about 1? Is 1 an interior point?
I don't think
Okay,
so, sir.
because around 1, all the rational numbers are not in the set.
Yes, all rational numbers are not in the set. Yeah, you are in the right direction. Then
Only some are in the set, so it is not the open set.
yes, then so let us say I want to prove that 1 is not interior point. So what do you do? How do you prove this?
Yeah, let me say 1 and the half can be the epsilon, but the 1 plus half by 2 cannot be in the set in this set.
Yeah, you don't have to fix because open set says that small enough epsilon, right?
Yes,
Okay.
sir. But,
So
yeah.
So it's like you can take any small enough epsilon. In the rational number, you will get many rational number. Okay, which is not inside this, which is not inside this set S. Let us say this was the set S. So that's the problem, right? So we don't get for a small enough epsilon. I mean, for any epsilon, it's not about small only, right? It's like any, I cannot find any epsilon. Because the moment you will say that take bigger epsilon, whatever, like there are so many points within this, right? Within half and 1. Right, because there are points that are going dense towards 0, right? So let us say this point is 0. So there are many points dense, but then after that it's very scattered. Okay, and then it's 1 here. Okay, so the problems are like these points can never be interior points in Q because there are infinitely many rational numbers between them. So no matter how small I do, I always get so many rational which is not yet covered in this sequence 1/n. So that's the problem here. So what I'm trying to say is this in openness and closeness is also it's a relative property. Okay, so what is your ambient space, like what is your parent space, and corresponding to that you say whether it's open or not. Okay, So these are like further examples. Find the interior of the following set. So this is like you have to find the interior set. Okay, so you will find a set of all interior points of this and set of all interior points of this, and that will be called the interior of the set. So the interior, there is something called interior point and there is something called just interior. Okay, so set of all interior points is called interior. So what do you think is the interior of this?
-1 to 1 open set.
-1 to 1 open. And interior of this?
Sir, union of one union, half union, 1/3, and so on.
But is one interior point? Because in the interior we should only put interior points, right?
So will there exist any interior for this?
Yes, that's what I'm asking.
Union, half to
that's what I'm asking. Does there exist any interior point at all?
So in last slide we proved that there is no, like, these points are not in open interval, so I don't think there will be any interior for this.
So there is no interior point for this. Yeah. So interior would be empty for this. Okay.
So only open sets have interior.
Open in an open set. Yeah, open set, all points are interior.
So only open set has interior, or
no. Closed set also have interior. This was the closed set, right? The first example is a closed set, right?
okay. Yeah, sure.
So this was closed, and the interior is this. Then we have to find the closure.
I mean, the boundary points is sufficient, right?
Yes. Okay. What did you say?
Just taking the set and removing the boundary points gives us the interior set.
Yes, you can also think like that. Yes. Because the only points for which you are also intersecting from the outside, those are creating problem for you, and those are exactly the boundary points you have. Okay. So in this case, closure, right? So closure is the set including the boundary points, right? So what are the boundary points for this?
1 and 2.
1 and 2.
So closed interval 1, 2.
So it's like closed interval 1, 2. And then in this case, as a subset of R, right? Okay. So in this case, what is the closure?
Closed set 1, 2, 3.
So this set union union 1, 2, 3, and union all the boundary points of this set. So what are the boundary points of this set? What are the boundary points? So what are the points in this set?
1, 2, 3 are itself the boundary points, right?
Points in this set. Let me write down this set, because point in this set such that if you take a neighborhood along this, so let us say some any neighborhood actually, okay, such that any B epsilon neighborhood around these points, it will intersect both this such that any neighborhood this such that there exists any neighborhood such that if I do B epsilon and intersect with this 1, 2, 3, this will be not empty, and if I intersect and, okay, so this is like and intersect with 1, 2, 3 complement, then also it is not empty. Okay, so this is the definition in case you forget. So what do you think? Obviously you have to check only for
1, 2, 3 itself are the boundary points, right?
Yeah, so you're right actually. So just to remark on what you are saying, in this case 1, 2, 3 itself are boundary points, because if I take 1, then the ball around 1, and it's saying any, right? So even no matter how small ball I take, B epsilon 1, okay, it does contain 1. Okay, so 1 does belong, because 1 is the center of this, right? So B epsilon 1 intersected with 1, 2, 3 for any epsilon does contain 1, because 1 is the center and this is there. And if I take a intersection with the complement, right? So if I take a intersection with the complement, what do I get? 1, 2, 3, and complement, right? So 1, 2, 3 complement will be something outside, right? So 1 is like this here, right? And I have taken and for any epsilon ball I take, and 2 is here and 3 is here. So now I am intersecting with the complement, right? So it is indeed intersecting with many other points in the real line. So now the complement of these are the other points other than 2, and which is what it is intersecting. So take one of these points. So this is indeed again not empty. Okay, so like just visualization itself is enough, right? So I take any, however small I take, right? I intersect 1 itself, but other than 1 also I intersect something from outside, right? Similarly, this happens with 2, this happens with 3. No matter how small neighborhood I take, I intersect with a set containing 3 because the center of the ball is at 3, and I also intersect something that is in the complement. So that's why all of these are boundary. So closure of this is the same set because nothing extra we got. These are exactly the boundary points. Okay, so with this, I think we can stop here today because it's now close to this. I may take some of the tutorial classes or something like this, or extra classes, just to because these are the things like goes into usual UG courses, but I'm doing this just to keep things intact. But let us mentally prepare for 2 extra classes so that I cover the other interesting things that that you are hoping to learn in this course, right? Okay, so with this we will stop. Okay, thanks.